My name is Kendall Lam, and this is Lab 2, Lines of Charge. So for the purpose of this lab was to use a line of charges to computationally model the charge tapes in order to calculate the net electric force on the top tape. The models were the experimental model and the closed script computational model, and the preview of our results was that the estimated charge on one tape was 5.06 e to the negative 9 coulombs. So for the main physics concepts, the two important ones are electric field and the electric force on a point charge, and we use these two concepts in order to find the net electric force on the top tape. We also use Newton's second law, F net equals change in momentum over change in time, because the tape was not moving, so we wanted to find the forces. We wanted to set the gravity force equal to the net electric force, and we also use the principle of superposition, which says that the net electric field equals the vector sum of all the other fields. So for the experiment and the initial conditions, the first lab had the result being the charge was 1.623 e to the negative 9 coulombs, and we're using the same experiment for this lab. The system is a piece of charged tape, tape B, and the surroundings are earth and tape A. The initial conditions are that both were charged with unknown positive charge. So for the lab 2 model, we also assumed that each U-tape had about the same amount of charge, but instead of it being a point charge like in lab 1, we modeled it as evenly distributed along the length of the tape. So for the coding, you can see here is just defining the physical concept, putting the mass of the tape, and this is the estimated net charge on one tape. And this is a function that tells the electric field of a charged particle at a certain observation location. And so this is a function that creates basically a line of charges to model the tapes, and right here you can see that we set both the top tape and the bottom tape to this line of charges, and we set the vector for the top tape a little bit higher, around 1 centimeter above the bottom tape, because that's what we had in our experiment. And so continuing on, we want to find the net electric force on the top tape as well as the electric field at each of the pieces of charge of the top tape in order to find the total net electric force. So we iterate through each piece of the charge in the top tape, and for each piece of that charge, we iterate through all the bottom tapes in order to find the net electric field at the position of that piece of charge in the top tape. And after that, we're able to find the net electric force vector by creating an arrow, and we also create an arrow for the gravitational force vector. So for the results, this is what it looks like when you run the program. You can see the net electric force and the gravitational force are equal and opposite, which makes sense because the change in momentum over change in time, the net force was 0. So all these green arrows are showing the electric field arrows for each of the pieces of charge. And so for the comparison, you're going to see that the new Q is 5.06 e to the negative 9, which is about 3 times greater than the charge in lab 1. And the difference is that this time we had lines of 100 charges versus 1 point charge modeling tape, so our model here is more accurate. For sources of error, we made a lot of assumptions for this lab. The number of charges we modeled is not the same as real life, and tapes may have had different charges. The length of the tapes were not exactly the same in the experiment, and measuring distance was not very precise. So those all could have affected the results. And what if you had modeled each of the tapes as a single point charge like in the previous lab? We already saw that the Q was lower in the lab 1, and new Q is about 3 times greater, and that's obviously because of the different modeling of the tapes. In lab 1 they're point charges, and now they're line charges. So the second model more closely models real life and is more accurate. Thank you for listening.